What is big science? Big science is the name given to the gigantism of scientific enterprises. It is usually associated with post-World War II and post-Manhattan Project work. The Manhattan Project is generally reckoned to be the beginning. It had 200,000 people working for it, which was as big as the U.S. car industry. But various other projects of that era, especially radar, was also seen as big science. Big science projects after World War II were mainly in physics, such as particle accelerators, the space program, and fusion experiments. They were administered often in university settings or in separate institutions overseen by universities, and they were funded by public agencies such as the Department of Defense or various civilian bodies such as the Department of Energy, National Science Foundation, or the National Institutes of Health. They made science into a managerial endeavor. Big science institutions can contain tens of thousands of people. So what is bigness here? In one sense, sheer scale suffices, but in another, some of these projects are actually combinations of lots of small offices. What is central in this respect is a different nature of science, one that stresses teamwork, hierarchy, management, and technology. With teams composed of hundreds, not a few people, and it also involves focusing on large numbers of people and resources on one experiment. This was often controversial because it changed the life of science. It involved compromises with review committees, compromises with Congress, with the military, institutional politics, and so on. Some scientists, as well as outsiders, complained that big science inaugurated a factory style that suppressed imagination and creativity, and replacing them with an approach that prized throwing big money and big technology at a problem. However, the beginnings of big science didn't happen with the Manhattan Project. In the United States and the United Kingdom, nuclear research began to get big in the 1930s. Earlier still, World War I saw the development of military-industrial academic cooperation devoted to chemical research. This then became part of a public fascination with large projects in the Depression: Golden Gate Bridge, Hoover Dam, and the Empire State Building. Also, the public was concerned to invest for social good. In this sense, early big science was symbolic. One aspect of this was pre-World War II sponsored research, often directed toward getting patents. And increasingly, researchers resented this dominating their work. Rather than looking for new discoveries, they looked for patentable ones. So when World War II began and the state moved in, this was seen first as a release from commercial constraints, even though state and military secrecy applied. But the distinction wasn't always so great. For instance, DuPont brought industrial techniques to the fashioning of nylon. During the Manhattan Project, the manufactured plutonium, on which half the project depended, was contracted out to DuPont. It used its skills in making nylon at a new plant in Hanford, Washington, which cost $350 million. It imposed a factory management style on scientists who objected to that work. But how and why did big science develop in the 1930s? The answer is that this was the era of the Depression, the era of mass unemployment, the era of breadlines, of immiseration in cities and especially in the countryside, and especially in the case of the Dust Bowl. The political and social solution to this was the era of big government involvement in solving problems. There were social and technological answers to these problems. In the case of the social, there was Social Security, there was the FDIC, there was the FHA. The New Deal focused on a number of things, including trust busting. It focused on banking stability. It focused on making sure through the Federal Reserve that banks didn't go under. It focused through the FDIC and making sure that your individual deposits in banks were insured. It focused on the FHA to make sure that mortgages were extended and secured to individual homeowners. In addition, the New Deal brought Keynesian economics to American society by focusing on expansion and consumer demand. Further, the New Deal brought a focus on public works through the lettered agencies, that is, the CCC and the WPA. The WPA stood for the Works Projects Administration, which promoted both economic relief and reform. It chose projects which would not compete with private businesses, and did a number of things such as paving streets and highways, building bridges and airfields and post offices. It restored forests and extended electrical power to rural areas. Over its 7-year history, the WPA employed about 8.5 million Americans. In addition to building the nation's infrastructure, the WPEA also funded unemployed artists and authors to promote American culture. This appeared through the federal theater, arts, music, and dance and writers projects, and it brought the arts, music, and drama to the smallest communities and sponsored public sculptures and murals and commissioned noted American writers such as John Steinbeck, Richard Wright, John Cheever, and Claude McKay to write regional guidebooks and histories of the American people. The efforts of the WPA marked the first time that the federal government tried to support and actively promote American art and culture. Public works also included infrastructure, for instance, the Hoover Dam, which was built in 1935. One special place where New Deal public works occurred was the Berkeley Radiation Laboratory, which was a cyclotron. It also drew from Works Project Administration and the National Youth Authority, which put electricians, machinists, carpenters, and other technical assistants to work in the radiation laboratory on the government payroll. The Depression also produced a steady supply of physicists willing to work for nothing in order to learn cyclotronics. From 1933 to 1940, the Rad Lab had several graduate and postdoctoral students paying their own way to work at the lab. They helped the Rad Lab staff grow from a total of 10 in 1932 to 60 in 1939. Further, the laboratory had private funding from the Rockefeller Foundation. In the 1930s, the Rockefeller Foundation devoted enormous amounts of money to research on medicine, specifically curing cancer and to study proteins. The Rockefeller Foundation's report on this research stated as follows: "Science has made significant progress in the analysis and control of inanimate forces, but science has not made equal advances in the more delicate and more difficult and important problem of the analysis and control of animate forces. This includes the desirability of greatly increasing emphasis on biology and psychology and upon those special developments in mathematics, physics, and chemistry which are themselves fundamental to biology and psychology." This invitation was to use the power and direction given by Rockefeller grant allocations to reshape the human sciences by reference to the physical sciences. The payoff from this reductive program seemed glittering. The challenge of the situation is obvious. Can man gain intelligent control of his own power? Or, as the Foundation put it, can we develop a sound and extensive genetics that we can hope to breed in the future superior men? Can we obtain enough knowledge in the physiology and psychobiology of sex that man can bring this pervasive, highly important, and dangerous aspect of life under rational control? Can we unravel the tangled problem of the endocrine glands and develop, before it is too late, a therapy for the whole range of mental and physical disorders which result from glandular disturbances? Can we solve the mysteries of various vitamins so that we can nurture a race sufficiently healthy and resistant? Can we release psychology from its present confusion and ineffectiveness and shape it into a tool in which every man can use every day? Can man acquire enough knowledge of his own vital processes so that we can hope to rationalize human behavior? Can we, in short, create a new science of man? These were the questions the Rockefeller Foundation asked. So now we can see why the Rockefeller Foundation would want to know the structure of proteins. It was part of an audacious hope to re-engineer society from the bottom up. The shape of proteins was the first impression of the shape of things to come. Before big science, the old style of small science was epitomized by tabletop equipment. A common enterprise in the 1930s was bombarding targets with neutrons to produce new elements. In 1934, Enrico Fermi found that when uranium was bombarded, it produced several different elements. In 1938, this was confirmed to involve fission. In 1939, Otto Frisch and Lisa Meitner reported that this also gave a lot of energy. This generated the question, can you use the released neutrons to produce more fission, and hence a chain reaction, thus releasing tremendous energy? The possibility of chain reaction was rapidly confirmed on April 22, 1939, in a letter to Nature by Pierre Joliot Curie, which said that each fission of an atom produces 3 or 4 more neutrons. This meant that a bomb was possible. Subsequent crisis meetings in various capitals all over the world happened. In Berlin, all of existing stocks of uranium were commandeered. Newly captured mines in the Czech Republic were told to obtain more. The British soon heard of the secret meetings and concluded that Germany was working on a bomb. In September 1941, Werner von Heisenberg, who was running the German bid for the bomb, and who had a working atomic pile which could produce a ton of uranium every month. In October, Heisenberg went to talk to Niels Bohr in Denmark, which was then occupied by Germany. Bohr conveyed this to the Allies when he escaped to London 2 years later. Meanwhile, in 41 and 42, Hitler had decreed that German science would be subordinated entirely to the war effort. And in fact, this subordination stymied the bomb project. In the United States, scientist Leo Szilard collaborated with Albert Einstein for two reasons: to write a letter to Roosevelt in order to encourage the Belgians to guarantee the uranium for the United States, and second, to persuade the United States government to begin research on the atomic bomb. Roosevelt endorsed the project, but had drifted for 2 years. In July 1941, a group of UK scientists came to the United States. They persuaded E.O. Lawrence, who was running the cyclotron at Berkeley, who then buttonholed James Conant to Chicago. Conant and Vannevar Bush together persuaded Roosevelt to redouble efforts on building the atomic bomb. By this meeting, October 9, 1941, the scientists were licensed to go for a bomb at full speed. The assumption was that the Germans were advanced, and given the nature of German science, they wouldn't be doing it unless they thought it was possible. At first, Oppenheimer and Lawrence thought that it would take 100 kilograms of U-235 to make a bomb. So Lawrence converted his cyclotron at Berkeley to making this isotope. In order to make a bomb, the uranium needs to be brought together quickly to reach a critical mass, but it needs to avoid pre-detonation. What this means is that the critical mass needs to be assembled quickly, such that it doesn't get hot and explode in the way that we would see in a dirty bomb. That is, we want a real nuclear bomb, not a dirty bomb. In May 1942, Robert Oppenheimer was put in charge of the program. By June of 1942, the program was established as the Manhattan Engineering District. Originally, Oppenheimer visualized about 100 people working on the project. It became thousands, mainly young, mainly male, with a vast support staff. When they built the bombs, they envisioned two different kinds. One would use uranium-235. It needed to be separated out from U-238, which was very hard. U-238 is the kind of uranium that occurs naturally in nature, and the difficulty is that U-235 and U-238 are chemically the same. So no chemical separation process will work. What they needed was a gaseous diffusion plant that would separate, using electromagnets, a gasified form of uranium. The Manhattan Project built at Oak Ridge, Tennessee, a plant for doing this. It was a half a mile long, or 42.6 acres under one roof. This is a problem of industrial scale, which actually explains why it's very, very hard to hide the production of weapons of mass destruction. For the bomb using U-235, a gun method was envisioned for assembling the critical mass. The mass would be assembled in a linear fashion using a mechanism where a pellet of uranium would strike a target of uranium. This method was never tested because the scientists had high confidence it would work. Ultimately, a bomb of this design was dropped on Hiroshima on August 6, 1945. The problem was that Los Alamos needed to produce more than one bomb for it to work, politically and militarily. Making one gun-type bomb wasn't that hard. However, there wasn't enough U-235 around. The second kind of bomb would use plutonium, an element which was not confirmed to exist. But a big plant in Hanford, Washington, would make it. This would require a smaller critical mass than used in the uranium bomb. Originally, they thought to use a gun mechanism to trigger the explosion, but this proved impossible because plutonium explodes much more easily than U-235, and they faced the problem of pre-detonation, that is, the problem of the dirty bomb. So they needed to design a mechanism which would assemble the critical mass much more quickly, and so you used an implosion mechanism instead. Therefore, the Los Alamos Project needed a large group of scientists and explosive experts who would design a bomb out of conventional explosives that would create a perfectly spherical implosion wave. That implosion wave would compress the plutonium into a critical mass. The problem was to design explosive lenses that would produce a perfectly symmetrical implosion. So the Los Alamos Project needed, in addition to physicists, also chemists and experts in conventional explosives. This together would make for a contraption for making a bomb for plutonium, which was tested at Alamogordo, New Mexico on July 16, 1945. The bomb that came from this design was also known as the Fat Man because it was spherical, unlike the gun design, and this bomb was dropped on Nagasaki on August 9, 1945.